Hello, today I will be talking to you about another reaction of alkenes. It's going to be called Halohydrin Formation. In a previous video, I talked to you about addition of halogens to alkenes, and we saw that chlorine or bromine adds anti, one up and one down across a double bond, and the double bond becomes a single bond. Well, that's if you do the reaction not in the presence of water, but if you add a halogen to an alkene in water as a solvent, or at least in the presence of water, then something slightly different happens, although it's a very closely related reaction. So we add halogen in water, and sometimes this is thought of as addition of HOX, in other words, hypochlorous acid or hypobromous acid, as HOCl or HOBr, and that's how they refer to it in the heading of the section in the book that I'm going to ask you to read, section 6.3 on pages 221 to 223. And so just so you don't get confused, it's the same thing as adding Br2 or Cl2 in water to an alkene. As I said in the last reaction, that was video 6.05, we added a halogen to an alkene, and the two halogens added across double bond that you may remember is an anti-addition, so one up and one down. And the mechanism for that reaction involved forming a halonium ion, in other words, a three-membered ring with a halogen positive, a very strange intermediate that you would not necessarily think of as a particularly stable thing. A, because it's got a three-membered ring, which isn't particularly stable, and B, because it's got a positive halogen, and as you know, halogens want to be negative. But what we're going to see is that in halohydrin formation, instead of treating the alkene with halogen by itself, we treat it with halogen and water, as I said. Instead of adding X2 across the double bond, so in other words, two halogens, we add XOH, in other words, a halogen and an OH group. It's still anti, unlike the previous reaction where you just added two halogens, and so it really didn't matter which carbon gets which thing. In this case, we're adding a halogen and an OH group, and so it does matter which carbon gets which thing. So we're going to have a rule, something like the Markovnikov rule or anti-Markovnikov, to help us decide which carbon gets which thing. And we'll talk about that here in just a minute. One additional difference is that when you add halogen across the double bond, there's no byproduct. But when you add halogen and water, one of the halogens and an OH group add to the double bond, and what's left over is a molecule of HBr or HCl. So let's talk about the regio specificity. So if you add Cl2 in water to this molecule, notice that one of these two is going to get the chlorine and one of them is going to get the OH. I'm going to go ahead and tell you what actually happens. This is data, not theory. What actually happens is that the OH group adds to this carbon and the chlorine adds to this carbon. In other words, that's the more substituted carbon. We might call it the more interior carbon, or it's a tertiary carbon. And so that's where the OH is going to go. The less substituted carbon, the one that's less crowded, so to speak, is the one where the halogen ends up going. Let's take a look at this molecule. Different case. This one happens to be drawn as a stick figure, whereas this one was drawn in a condensed formula. But what happens when you add bromine and water here? Same idea as chlorine, really no difference between them. Which carbon gets which thing? Well, it turns out the more interior one, this one, in this case tertiary, gets the OH group, and the less substituted one, in this case it only has two hydrogens on it, that's the one that gets the halogen. So same regio specificity. More substituted carbon gets the OH. So in this case, it doesn't matter because the two carbons are the same as each other, so one chlorine and one OH. In this case, it does matter. The one that's more substituted gets the OH, the one that's less substituted gets the bromine. By the way, is there a name for a rule like that? Well, it's kind of like the Markovnikov rule, but notice that neither of the things we're adding is a hydrogen, so we can't really say the one that has more hydrogens gets the hydrogen because one's a chlorine and an OH group. So what we have to do is just sort of come up with our own named rule for it. Call it the Armstrong rule if you want, but basically it's saying that the OH will end up on the more substituted carbon or the more crowded carbon. Okay, the other thing we need to worry about is stereospecificity, and as I said, this reaction always goes anti, just as the halogenation reaction does, and we'll see there's a reason for that. It's essentially the same mechanism, but notice in a ring system you can tell where the chlorine is and where the OH is in terms of up and down, and if you use cyclohexene, you get the chlorine and the OH trans to each other, one up and one down. In this case, chlorine down and the OH up. And of course, you get an equal amount of its enantiomer, which is chlorine up and OH down. Same thing here. The OH and the bromine end up opposite sides, so the OH is down and the bromine up, or the OH up and the bromine down. And again, you get 50-50 mixtures of these two because this is achiral, this is achiral, all this stuff is achiral, and so you cannot create optical activity. So if you're going to get a chiral molecule, which this is, you have to get an equal amount of its mirror image to keep the optical activity zero. Okay, so here's the mechanism. As always, as we've seen in the past and we'll see in the future, you have to understand the mechanism to try to explain why you get a particular regiospecificity and a particular stereospecificity. So here's the mechanism. It should look kind of familiar. In fact, the first step is exactly what you learned in the previous reaction. The Cl2 or Br2 approaches the alkene, sits down on top of it, forms a three-membered halonium ion, which we talked about a minute ago, with a positive charge on that halogen. And then what would happen in the halogenation reaction, the X- would come in and attack one of these two carbons, and we didn't worry about which one it attacked in the previous reaction because both halogens are the same and you really can't tell and it doesn't matter. But now instead of the halide attacking, it's the water that's going to attack. Does it attack on this carbon, which is more crowded, or on this carbon, which is less crowded? We already know the answer. We know the OH ends up on the more crowded carbon. That seems weird. It seems like the water should attack the less crowded carbon for steric reasons. But here's why it actually attacks the more crowded carbon. Turns out that bond between the halogen and the carbon is highly stretched, with a lot of the electron density already being on the halogen because of that positive charge. These electrons are really pulled off towards the halogen. Same with these electrons here. So these bonds are really stretched out. And that means these two carbons are partially positive. They're carrying a lot of the positive charge that's shown actually on that halogen. So whichever one actually has more positive charge is the one that attracts the water better. And since that's a more highly substituted carbon, secondary better than primary, it attacks there. So the water attaches at that point. And we can see that it's anti-stereospecificity due to backside attack, as we talked about. The same thing is true for the halogenation reaction. It's anti-stereospecificity because the halide attacks from the bottom, pushing out the other halogen, and you end up with the anti-orientation. And its regiospecificity is such that the OH ends up on the more substituted carbon. And again, it's for the reasons that that carbon, when it's in the halonium ion, is a little bit more positive, and therefore the water tends to attack there a little bit more. Anyway, that's what happens in the second step. The water attacks, but we're still not quite done because the water has still two hydrogens on it, as it did when it was just plain water. That hydrogen doesn't come off of there until the third step. So in the third step, the halide ion that's been hanging around here, the halide ion is still there even in the second step. It's just, I didn't draw it in here because this I drew as a net ionic equation, but the halide is still there. So now the halide comes in, pulls off an H plus from the what used to be the water molecule, that then becomes a neutral OH, and the HX molecule is formed. So three steps: formation of the halonium ion, attack of the water on the more substituted carbon, and then the halide pulls off the H plus. And again, as I've said here, the regiospecificity is due to attack by water on the more crowded carbon. Again, seems weird because it's more crowded, but the reason is because it's more positive. Now, what about this HOX? This is the terminology or the symbolism they use in the book in the heading for section 6.3e. Well, it turns out when you dissolve chlorine or bromine in water, it reacts with the water. This is not an organic reaction. This is an inorganic reaction. It's just the halogen molecule reacting with the water molecule, and it forms two new molecules, HOX and HX. In other words, essentially, the water breaks up the X2 molecule. Part of the water goes with one of the halogens, the other part of the water molecule goes with the other halogen, and you get hydrochloric acid and hypochlorous acid. So, halogen in water is sometimes referred to as HOX, or HOCl, or HOBr. Has practical purposes in your life, because if you ever bought bleach or used bleach in your house, that is essentially chlorine dissolved in water, and so this is sometimes referred to as a bleach molecule, HOCl. This is actually in equilibrium, so that some of it is actually in the chlorine form, some of it is in the HOCl form. And by the way, that also happens in swimming pools. That's why swimming pools have that chlorine smell. That essentially finishes the lecture for today. Thank you.